Once again, here's the activity selection problem where our resource bike is available from 0 a.m. until 4 p.m. And then we have these 11 different customers who would like to reserve the bike. Say we use Sij to denote activities that start after AI finishes and before AJ starts. So this is the symbol that we are going to use. Say the first activity that we are going to choose as I is this one. And let's say we choose this activity as our activity J. Then Sij will denote all the activities that start after I finishes and before J starts. So let me remove all the other activities. So we've removed all the activities that are incompatible. Now this set of activities, 1, 2, 3, 4, and 5, represent Sij because these are activities that start after I finishes and before J starts. Now suppose that we would like to find from this Sj the maximum subset of mutually compatible activities. And say suppose that such a subset of mutually compatible activities is Aij. Aij. So this is a subset of Sij, which is our optimal solution. So this is also our optimal solution. Now say that this optimal solution includes an activity AK such that this is a part of the optimal solution. Now we could express our optimal solution Aij in the following way. Aij is equal to all the activities that finish before AK starts, Aik, combined with this activity AK, and all the activities that start after AK finishes. So this would be AKJ. Now looking at the maximum size of this optimal solution, we could say that the number of elements in Aij is equal to the number of elements in Aik plus the number of elements in AKJ plus 1. This is the AK that we have. Now essentially what we have done is broken down the length of our optimal solution. That is, in order to calculate Aij, we can calculate Aik and also AKJ. That is, if we have an element AK, an activity AK that falls within the optimal solution, then we can actually break down the calculation of the size of the maximum number of elements into two problems. Now let's check if such a breaking down or splitting of our problem is actually valid. In other words, what we want to ask is AIK optimal solution for my set of activities SIK? So all the activities that start after I finishes and before the activity K starts, for this set, is AIK the optimal solution? Now let's say we assume that AIK is not the optimal solution, and let's say AIK dash is the optimal solution, which obviously should be greater than AIK, because if it was smaller than AIK itself would be the optimal solution. Now, if this was the case, then what this means is that the length of AIK should actually be more than what it should be. In other words, this set AIK should contain more elements. And since we know that Aij is the union of AIK, AK, and AKJ, if this set was bigger, then the size of our optimal solution would be bigger. That is, Aij would not be the optimal solution. There would be something that would be added to Aij. This basically invalidates our original assumption that Aij is the optimal solution to our problem. So this means that this expression should be true. In other words, we can in fact break our problem of calculating Aij into Aik plus Akj plus 1, where Ak is an element in the optimal solution. So this proves the optimal substructure property of the activity selection problem. Say I denote this, the length of Aij using this symbol Cij, then further, with the help of this optimal substructure property, I can say that Cij can be expressed as Cik plus Ckj plus 1, assuming that this activity K is one of the elements in the optimal solution. Ak is a part of the optimal solution. When we don't know that an element AK or one of the elements in between I and J is a part of the optimal solution, we have to calculate all the possible elements AK. And to do this, we have to check for all possible values of K and then get the maximum. So in other words, I can say if I don't know the element AK, which is a part of the optimal solution, I can express the size of my optimal solution Cij as 0 if my input element set Sij is 0, or otherwise maximum of all possible elements Ak that belong to Sij. And for each of these activity AK, we would like to calculate the sum of Ci up to k plus Ck up to j plus 1. And this is if Sij is not equals to 0. In other words, for each activity in between I and j, I want to pick that activity and then see if the optimal solution before that activity and after that activity plus 1 gives me the maximum possible length. So this actually gives us the recursive algorithm to obtain the optimal solution. Now we can memorize it or create a bottom-up version as well.